Now let's look at these models and see how they go around calculating basically a mu t for us. The first one, which is Szilard-Almaras or SA model, this basically is a low-cost trans models, and it is solving a transport equation for modified eddy viscosity. So basically this uses one equation. It used to be a popular model, but we do not use it anymore, so we're going to just jump over it. Just know that SA model is a one equation old model. The most popular and most widely used equation is the K epsilon model. In K epsilon model, first off, you use two equations. So it's use of two equations instead of one equation. And so the K epsilon model is called basically K epsilon model because it uses two equations, one for K and one for epsilon, the kinetic energy and the dissipation rate, to calculate the turbulent viscosity. So in the K epsilon model, the turbulent viscosity is being calculated using two equations for K and epsilon. You see here, you have the mu t, which is of course related to you have nu t, which is related to mu t as this type of formula. Now if we dive into the K epsilon, there are different types of K epsilon models. They slightly differ in what they represent and what they are good for, and a slight difference in their equations. This KE or the K epsilon model standard is the most widely used equation as for solving turbulence, and model parameters are calibrated by using data from number of benchmark experiments. So basically these are two sets of equations that the constants in those equations are coming from benchmark experiments. You might say, have they done experiment for all the cases out there? Of course not. But when we talk about benchmark cases, we are talking about cases that are basically general enough that the result from them, the coefficients that come from them, are good enough for most of the cases. And so that's the basically standard K epsilon model is the to-go model that we will be using in this class. Also, you can use it later on in your projects. Then you have two other variations of the K epsilon model. It's called realizable K epsilon and the RNG K epsilon models. They are slight variations of the standard one. In realizable, the equation for epsilon is improved by better experimentation and more experimentation. And in RNG, basically, constants in K epsilon equations are derived analytically. So they are, instead of empirical, which means using experiment, they are coming from analytical solution. So what we discussed in terms of one term equation model, two equation models, so on and so forth, since they are models, since they are auxiliary equations, they have their own limitations. One of the common limitations between these models are near wall treatment. So basically, all of these models, once you get closer and closer to the wall, the treatment of the flow becomes poor, so the results becomes less and less accurate. So these models give good results further away from the wall, but not near the wall. So we have to basically do extra procedures to make sure our results near the wall are also as accurate as possible. First off, a very fine mesh will resolve the region. So that's one way of solving the issue with the wall. Yeah, of course, as my model gets less accurate, I can somehow compensate it by adding more cells and refining my mesh near the wall. But that's not basically very practical in a sense that you can't continue increasing number of cells. For that reason, we have to have some extra models, new methods for near wall treatment. So first off, we have to define something called Y plus. Y plus is basically a non-dimensional distance for a wall bounded flow. If you want to look at this Y plus simply, it's basically your distance from the wall by a non-dimensional sense. But it's defined by U star multiplied by Y divided by nu. You know what the nu is. Y is your actual distance from the wall, and U star is the friction velocity. The friction velocity is defined as below. But long story short, it's your non-dimensional distance from the wall. Now, if we look at Y plus based on U plus, which is U plus is also non-dimensional speed from the wall, velocity from the wall, which is divided by your actual U divided by your U star. If we look at this, the horizontal axis is your Y plus and vertical axis is your U plus. So this is basically the plot, non-dimensional plot of velocity as you go further and further away from the wall. The red line is the actual, what actually happens. So the red line is actually what happens, right? So the blue line, the straight blue line is called the log law, and the other one is the linear ones. And since this is exponential, that's why your linear line is curved. And as you can see, we can define this based on how good the blue lines are the models, how good the blue lines adhere to the red line divided into three zones. In viscous sublayer, your log law is a good model. In log law region, in viscous sublayer, your linear is good. In a log law region, your log law is very good. But in the buffer layer zone, which is around Y plus of 11, none of them are working very well. Now let's look at, have this in mind, and we will look into actual equations for this. So there are different near wall mesh requirements and near wall treatments. One is called, actually the first two are standard near wall treatment and non-equilibrium wall functions. So basically in this, what happens is you take the buffer and sublayer, these two layers, box them together, and instead of actually resolving them using your equations, you just assume it as a black box and use auxiliary equations, extra auxiliary equations for it. Which means your first layer of cells is much higher than these two zones. For that reason, wall adjacent should have Y plus value of 30 to 300, meaning it should be way above 11. In enhanced wall treatment, basically what happens is you actually resolve all the buffer layer and sublayer using your mesh. This is more complex method, and your Y plus of your first layer of cells should be less than 5. When we say the Y plus for your first layer should be more than 30 or less than 5, meaning the non-dimensional height of your cell should be 30, or Y plus of your cell should be 30 or more. So long story short, standard wall function works with simpler flows, whereas enhanced wall treatments works very well with complex flows. But generally speaking, you always start with standard wall function because that's the standard of the industry, and you would get actually fairly good results with that for almost most of the problems. If it's not, if it doesn't satisfy you, the results, you can build up on that result and change your turbulence model to enhanced wall treatment. So now what I'm going to do in here is I'm going to show you, let me pause it. So what we discussed to this point was actually RANS model. So these were RANS models and of course subcategories of RANS model. But now I just want to show you the LES modeling. And remember, in LES modeling, you resolve the large and medium sized eddies and you basically model small scale eddies. This is an engine of this is a prediction of supersonic jet noise using unstructured LES. So this is basically flow coming out of a jet engine. I know it's not. We have to, and it's not done by us, of course. Yes, this is the jet engine, and this is done by LES modeling. So this is the exit of it. So this is the actual flow and the heat coming out. So this is the actual flow and these are the temperature contours. So you can see this is done by LES. And that's the core temperature. And the blue lines, blue waves are actually not related to our cores, but they are basically noises. So it can also do acoustic on this system. But what is interesting for us is the LES modeling at the exit of our jet engine. Okay, the next method is direct numerical simulation, or DNS. As you remember, as we discussed, DNS is basically solving our existing 5 equations, meaning 3 velocities, continuity, and energy equation, without any per se, without any auxiliary equation. So you just right away go ahead and solve those equations. The trick with this one is you need to have, as we said, a very, very, very refined mesh. And of course, a very refined mesh means a very powerful computer, many very powerful post-processing softwares and memories and so on and so forth, right? So in DNS, the 3D unnecessary Navier-Stokes equations are solved numerically, basically by resolving all the scales. But this, as we said, very time consuming. For example, for a simple geometry's modest Reynolds numbers, DNS has been done successfully, but it has a very high number of cells. For example, for a channel flow between 2 plates, very, very simple flow, it's around 10 million cells. Now you can see the enormous cost of doing DNS, and that's the reason everybody has turned into other methods, auxiliary equations, and RANS models, because it's practical, it's easy. I mean, easy considering DNS. It gives you good enough results that you can do whatever you want to do in your projects. But this is a simulation of direct numerical simulation result. This is the column of smoke, and suddenly it's being disturbed and start disintegrating. And this is not a movie, this is a simulation, but it's a DNS simulation, extremely heavy one, as you can see, and it resembles honestly everything than simulation. It looks like just a real thing. So now Let's have a quick look at some in couple of slides before we finish this, at some ANSYS specific settings for our turbulence modeling. So as you increase the number of models, as you put more auxiliary models for your simulation, you have to provide extra relevant information in order to make the software capable of solving it. So when you add basically the turbulence modeling, you need to provide the corresponding boundary conditions. You can provide k and epsilon. You can provide direct numbers of k epsilon, but usually that's a difficult thing to do, because unless you have some sort of experiment, it's very difficult to provide numbers for k epsilon, because usually these numbers, they come from experimentation, and unless you have done some sort of experiment, this is not possible. So if we don't have the numbers for k epsilon, what shall we do? There are other options for us. So you can provide turbulence intensity and length scale. Usually length scale is related to the size of large eddies that contains most of the energy. So you can provide these two, which is the turbulence intensity and length scale. Turbulence intensity comes basically in terms of percentages, and shows what is the percentage of turbulence flow coming into the inlet. Usually there is no definite number that you can calculate, but usually this number is between 5 to 20%, which means some sort of low or modest turbulence coming from the inlet. And usually we do this because we want to let the turbulence happen inside the system rather than outside. So the other method is turbulence intensity and hydraulic diameter. This is the most common method we use, since for turbulence intensity we usually give a typical number around 10%, and hydraulic diameter either at the inlet or at the outlet can be basically easily calculated. So this one, especially for cases that you have a duct flow or pipe flow, that the hydraulic diameter is can be calculated easily, you use this one. And the other one is, of course, turbulence intensity and turbulent viscosity ratio, which is mu t over me, which is usually a number between 1 and 10. And this is again between 1 and 10, doesn't come from any calculation. Rather, it's an accepted benchmark for the industry. But also this one is also difficult because you don't have a number for mu t. So I would say you will stick to the turbulence intensity and hydraulic diameter. So the recommendations are to start calculations by performing 100 iterations or so with standard k epsilon model first, of course, and first order upwind. Then move on, then build up from that, perform more iterations using the result of the first set of iterations. So always and always go step by step. So here the last two slides, basically I have included some informational graphs, some informational charts about different models, the SA model, the standard K epsilon model, the RNG K epsilon model, and realizable K epsilon model. There are two other models, standard K omega and SST K omega, that we didn't discuss, but these are basically based on kinetic energy and the vorticity, but they are not very common. That's why we didn't discuss in this class. And I would say you should focus on these three models: the standard, RNG, and realizable K epsilon models. Again, here you can I have summarized for you basically the pros and cons for each of these models. Again, you don't need to memorize this, just read it out and have the general parameters in your mind. Okay guys, this is done. Thank you very much. Please review this in full before the class on Friday. Friday I will be answering some questions and also going over general items of this presentation. Thank you very much.